All right, everyone, welcome back. We are at hour 15, and I think that's hour 15 anyway. So this marks, if this is hour 15, this is exactly 1/3 of the lecture is now done. And I have to admit, I'm kind of running out of video gags. I don't know if you noticed the one time that I filmed the scene backward and then reversed it in the video. I don't know if you noticed that, just for a second. Anyway, I'm kind of running out of ideas, but I'll think of something. I'm guessing I hit a dry spell for a while. So we're just beginning our middle part of this class, being defined as after the first test, second, before the second. Quantum mechanics here on out. You definitely need to stay on top of this because we build up and build up. No particular day will be too onerous, but it builds up and builds up. When we get into lecture 3, we'll have a little bit of an outside topic in kinetics, but even then we'll still be on quantum. And I guess there's just not much to say. It's kind of funny is normally after the first exam, everyone's kind of crazy and tuned out, and maybe you are, but I wouldn't know it. So it's like one time it's slightly easier for me to do this. And as I mentioned, also reviews will be less comprehensive as we go along. So if you didn't watch last lecture, or it's been a while, if your timing is as messed up as I am. See, I'm filming these way ahead of time because I know that things will happen and will just completely send me off in a different direction for a long time. So that's why I'm giving myself plenty of time, to make the videos look good. So I can't spend nearly as much time reviewing comprehensively. At this point, I'm only going to review what we did the last class. And last class, all right, well, we talked about the uncertainty principle, and homework questions hopefully will solidify that. Although I'll do an example problem today. And we also started talking about flat potentials. I formally introduced the particle in a box, even though we've been actually talking about that for about 2 weeks. Okay, anyway, I'm getting ahead of myself. So this is all about flat potentials. And the particle in a box, inside the box is a flat potential. Mainly is potential energy. Okay, so this is kind of funky. Potential of 0 counts. That's the free wave. Potential that's constant is also flat, right? So it's not like V is x squared, like a harmonic bond, right? That's a bond potential. That's not a flat potential, obviously. Now, the reason I'm saying that this is kind of funky is that we're going to do this next class, is that you can have potential surfaces like this. So here's x. You can have them take steps. And that still counts as flat. I know it's like it shouldn't, but it does. Now, the reason is that, let's say that's at x equals 0. Left of 0, it's flat, and right of 0, it's flat. So that's why it's still a flat potential. Anyway, you're going to see, we're going to spend 2 days on these things. So it's kind of important. All right, now, why is that important? When the potential is a constant, you can just bring it over to the right. Now, again, I'm not going to review everything in ad nauseum. You should be able to do this, hopefully, in your head right now. All I did was I brought potential energy over to the right, and since it's a constant, all it's doing is it's shaving off the energy. And I gave some examples of that last time, how a wavy wave, which is a wave function, hits a potential barrier, and it will get less wavy. And that's because it has less kinetic energy. Anyway, I brought that up last. Oh, here, I'm going to go crazy until I do it. Okay, wavy, 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 and then it hits a potential barrier and it gets less wavy. Okay, I just had to do it. And that's happening here. Okay, heads up, heads up. This is next lecture, but I have to tell you now, right? What can happen is the potential could be higher than the energy. So I've presented this as potential energy just taking some of the energy away, total energy. So you have less kinetic energy. Big E is potential plus kinetic. So if you have greater potential energy, then you have to lose on the kinetic. However, what you can have is potential energy is greater than the total energy, right? Now, what that happens in that case, let me show you what happens and I'll just redraw this figure. And we're going to solve for this explicitly, and the wave function just decays off. It just flattens out, it just dies. Okay, so we're going to solve that. I just want to point out that that's a possibility. All right, now, as I also said last time, and I think that's this Friday's lecture, for those of you who, to bolster your math, because remember, because of how weird all this is, I'll look at the homework and I'm getting a feel for you folks, and I remember what other questions people had. So I'll look at the homework and I'll see if I can do some things that are related. I also mentioned that I would show you exactly how the solution comes about. So every time you have a flat potential, this is always your solution. And I can show you the mathematics on how you do that. And you don't need to know that for the class, right? The extra hour is just exercises. It's just stuff to help you do better. So I'll try to think of some questions to do based on the homework, obviously, and I may show you that. You don't need to be able to solve that, but I just want you to see where it comes from. Now, the advantage there is just your comfort. If you look at something and don't feel that it's from Mars, especially mathematical formula, you're better off. You can focus on other things. If you see this on an exam and you say, oh my God, what the heck is that? I mean, you're not even able to answer the question, right? You're supposed to do something with this, but you can't even get that far. So that's why I hope that you want to see where this answer comes from. Now, in terms of what you do with it, as I explained last time, there are boundary conditions, and we're going to do this one maybe today or tomorrow. I can't even remember now. Last time we talked about how if A is B, then A could be like 1/2 and B would be 1/2. And then I'm looking at this and I'm saying, well, that's the formula for a cosine, right? Now, if A is minus B, so 1/2 minus 1/2, that's basically a sine. Now, I know it's technically 1/2i. 1/2i this minus 1/2i that, but the letter I doesn't matter because it would just come out in the normalization, right? And I'll make that a little bit more clear in a moment. I actually kept this from the last lecture. So what did we do with this? We solved the particle in a box problem, which goes from 0, this should be a little tick mark, sorry, from 0 to L. And we solved boundary conditions, right? The boundary conditions were that the wave function at x equals 0, the wave function is 0. And from that, we were able to solve A is equal to minus B, so we know that the wave function is a sine. And at x equals L, the wave function, I'm writing it down twice, aren't I? I don't know why I'm doing that. Anyway, the wave function at x equals L is 0, and that's how we were able to get these innards. You also could probably just look at this and figure it out, right? So I just drew the first 3 states: ground state, first excited state, second excited state. Of course, there's an infinite number of states. I could keep making the waves weightier as long as they had nodes at 0 and L. And I can see, our quantum number, which goes from 1, 2, 3, ... You see, I can just look at this and see sine pi x over L would be a half wave, right? I know that's a half wave because pi is half of a wave, right? Waves go from 0 to 2 pi. So if this is sine pi x over L, when x goes to L, sine has gone from 0 to pi. So that's a half wave. So I'm just telling you that because that's how I do it in my head. If n is 2, then I would have a full wave. And again, you would have the boundary conditions of being 0, 0 at x equals L, x equals 0 and x equals L. And the same for this one, for 3 pi x over L. You would still have the wave function being 0 at x and L. So on and on and on. Again, I mentioned how that's the ground state and that's the first excited state. You solve from this, either from just kind of looking at it and figuring it out, or boundary condition. All right, now I mentioned I mentioned that, I've said this a zillion times, I know I've been super repetitive because I mean, we've already seen the particle in a box a bunch of times, but it's really important and I want to make sure you get it. And that's why I like to preview all the time so that today you're already bored with it. It's good to be bored than confused, right? So I'm kind of biasing the class towards bored than confused. Okay, and when I ended last time, I think I said this at the very end of the lecture, that like either you could look at these waves and figure out that it's sine pi x over L, yada, 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 or you could do some formal derivations and get the exact same thing. It's not normalized. And if it's not normalized, when you do expectation values, it'll fail. You'll get the wrong results, right? Now you remember why? Remember how the expectation value is dependent upon the eigenvalue equation working, and it was also dependent on the wave function being normalized. If that didn't happen, you would not return the proper eigenvalue. It would not return the proper eigenvalue if the wave function was not properly normalized. So again, I know I said it a million times, so hopefully you're bored of me saying it, but we often figure out the wave functions without the normalization constants. Okay, now there's two ways to approach this, and I'll have the formulas on the cheat sheet on the exam. One is to note that what you're looking for, and I'll be explicit in this case, you're looking for a normalization constant, so we'll cleverly call that n, sine nx pi x over L. Notice that when I've written this, I'm not like solving only for the ground state. Okay, so what? What that means is that, God, how do I want to put this? One way that makes sense is to state that now instead of going from minus infinity to infinity, the particle in the box is only integrated from 0 to L because you assume the wave function is 0 everywhere else outside the box. So I just want to point that out. I'll point that out on exams because I don't want you to lose points messing that up because you would get lost at the very beginning. And what's the point of that? So anyway, okay, so you integrate the particle in the box from 0 to L. And wave function squared, remember it's the wave function squared that's a probability distribution, sine squared. So there you go. Okay, now what you do is you solve for n. So the way I tend to do this is I actually can, I just pretend that this isn't there, and then I use some software, which I think you've already been using that a little bit. I will just use some software to figure out what the integral is, and again, it's not going to come out to be 1. Now, actually, another way to do that is to take, here, let me do it this way. I'm going to take n squared outside of the integral, and therefore I know that n is 1 over the integral of the wave function squared. And I'll write all that out, just to be complete. And then you use some software. Okay, and so this is n squared, so I better put a square root. So I can see that I did not give myself much room. This was a little stupid of me. Okay, there we go. 1 over that. That is kind of scrunched, isn't it? Anyway. Okay, so again, however you get this in your head, but this could be, I would put this as like a formula on the exam. It's 1 over the square root of the integral of the wave function, the absolute value of the wave function, right? And in this case, and I never even said this when I first introduced this problem, why don't you try it? Actually, you don't have a choice because on the next homework, you're doing a bunch of particle and block stuff. And don't try to solve the integral of sine squared. I just hope you know what it is. You know, it's an area. it goes from 0 to L. I hope you get that. But if not, whatever. Just do it online, right? So, and I hope you'd be sophisticated enough to know that when you are looking at math problems, whatever math problem you have, you can always find the answer online. More and more, you can just type things into Google even, which is kind of cool. All right, so what do you get? So what you get is 1 over the square root. So again, I do some online this or that. L over 2. And therefore, the normalizer is the square root of 2 over L. There we go. And, all right, so this is, here we go, let me write it out. 2 over L. There we go. Should speed up time or something. Yeah, there you go. And let's see, okay. Because your next homework, you're going to do some uncertainty principle practice with the particle in the box. I'm going to just do everything I can think of, basically. You know, that's how, I mentioned this before. What you do with quantum mechanics is you often figure out the wave functions without the Schrodinger equation. And then what you do is you plug those wave functions back in, and you get as much out of it as you can. Well, you get energies, if you're working with the Hamiltonian. You can get momentum. There's all kinds of properties you can calculate. So that's basically what we do with quantum mechanics in general. Let's see, okay, now I have some room here. But say I thought I had to wipe the board out for a minute. Alright, so now in terms of what I'm going to do, I'm just going to throw everything I can at this thing. And why don't we do the Hamiltonian? So again, you know, the Schrodinger equation is usually thought of as the eigenvalue equation with the operator being the Hamiltonian. You would think that that would be your starting point for solving the wave function. It almost never is. Every now and then I've seen some problems like, I think harmonic oscillator, right, the bond one. That one you use the Schrodinger equation to solve the Schrodinger equation, and there really aren't too many others that you actually do that. So anyway, I'm prattling on now. Okay, so let's get the energy and make as many interpretations as we can. And in this case, I don't like to use expectation values. I want to do this the easiest way possible. Now, for average position and momentum, you're going to want to do that. For energy, with the Hamiltonian operator, I like doing it this way, with the particle in the box, because it's just way easier. Okay, so how do I do this? Well, write down. And you notice another reason that this is a flat potential. Notice that I'm not, I've just got this, right, now you should know that this is the kinetic energy operator, and 2 over L. I'll point out a whole bunch of, there's actually a lot going on here that could be very helpful to you. All right, in terms of like, is this still a flat potential problem? Notice that I didn't write plus V. I didn't write the potential energy times the wave function. That's because we're only thinking about being inside between 0 and L, and inside the box, there's no potential energy. Outside the box, where there is potential energy, you don't ever think about it because the potential energy is 0 and the wave function doesn't go there. It's kind of like cheating, right? But that's cool because it's easier. All right, so what do you get? Okay, so I'm going to keep, okay, so double derivative of sine, sine to cosine, cosine to minus sine. So the reason I'm saying that is I'm going to just get rid of that, I'm going to get rid of that minus sign. So I know that there's a minus sign. We've talked about that since the very beginning. The constants are still there. Okay. Now what's going to happen is, and again, I'm going to do this kind of quickly, because this, you know, you see why I'm trying to get your math, throw those math problems at you? What happens when you do the derivative of sine? Anybody? Just kidding. The insides come out, right? N pi, and the quantum number pi over L. that comes out once, it comes out twice. And so we're done, right? So nx squared, pi squared, not x squared, that's the one thing that stays inside. That little x is too small. When we think about y and z, we'll have an ny and nz, but that's coming up later. Okay, so, okay, now, of course, what happened to that square root of 2 over L? I'm separating it because remember, the thing that is hard about doing this with the eigenvalue way is making certain that you don't get confused where your eigenvalue is, which happens to be here. And so that's the energy. All right, here's the operator. Here's the operator. Here's the wave function. So you better get energy times the wave function. So again, the thing that's a biznknocker about the eigenvalue way is making certain like you don't accidentally put that normalization in with the eigenvalue. You see how you can do that? How you can just say, oh, that square root of 2 over L belongs over there. No, it doesn't. It belongs with the wave function. So this is the energy. Okay, so the energy of a particle in a box. Let me, you know what? The book puts it this way. All books put it this way. Let me just point out that, see, you're always going to see it this way, by the way. So h bar squared is h squared over 2 pi squared, 2 pi, the whole thing squared, 4 pi squared. So what you do is you take, you see you can wipe out if you, right, see that? If you insert h squared, so instead of h bar I'm writing h squared, then I just gotta divide by, the pi goes away, right? And I just end up with 8 L squared. Okay, so yeah, there you go. Now there's a whole bunch of stuff we can look from this. Okay, for one, remember that nx goes as 1, the quantum number, 1, 2, 3, yada, yada, yada. Okay. That means that there's always energy. So if nx could be 0, if that quantum number could be 0, then the ground state would have no energy. But it's not saying that. It's saying that there's always some energy to the ground state. Now, that is part of the uncertainty principle. If you have some idea of where it is, then you have to have a little bit less of an idea how fast it's going. If it's not moving, if it has no energy, it's not moving. And therefore you know how fast it's going. So you can't do that, so therefore the ground state has to have some energy. So let me say that again. I know that's a little confusing. If this was 0, the energy was 0, the only way to do that is for the particle not to move. If it's not moving, you know that, but you can't know that. You can't know where something is and how fast it's moving. Since that can't happen, it cannot be true that has 0 energy, right? So this is what you call 0-point energy. You remember, maybe you've heard of that before when you talked about kinetic isotope effect in organic lab. Now, organic class or lab, hopefully both. The kinetic isotope effect, which we're going to talk about later, is one of the ways that organic chemists figure out mechanisms. So I hope you've seen that before. This is basically just like that. There's always some energy, there's always some ground energy, and you may recall that CH bonds have a different ground state energy than a CD bond. So if you think that CH bonds are doing things in chemical reactions, then you replace them with deuterium and you'll get some differences because the energies, the ground state energies are different. So anyway, I'm just pointing that out. We're going to revisit that. Let's see, what else can I say about this? Okay, the energy is proportional to 1 over L squared. Now you may recall in our, when we were doing Heisenberg uncertainty principle, we did the example of position in Hamiltonian and that was not equal to 0. Now, hopefully you know what I'm doing here, right? This is a commutator, and the commutator is related to the uncertainty principle. If it's 0, then there's no uncertainty. But here, there is uncertainty. The commutator is not 0. Now that means that you can't know where something is and know what its energy is. That's basically the stuff I was just saying. All right, now, if L gets smaller, you gain certainty in its position, right? The smaller something is, right, I know I have a much better idea of where this particle is versus this one. Right? This one lives in a larger space. That one I know is simply right there, but this one, it has a little bit of room. Okay, this guy happens to have a smaller box, so therefore it has a higher energy. If it has a higher energy, then I would have less certainty in the energy. So again, you can see how the uncertainty principle is at work in the particle in the box. So again, let me just restate that. I know that was a lot. Energy and position have an uncertainty principle. You can't know where something is in its energy, just like you can't know where something is in its velocity, its momentum. And here you see that manifests itself as a particle in a smaller trap has a higher energy than one in a bigger trap. And again, we talked about that last time. I've actually been saying the same thing over and over again in different ways. Let's see, I think that's about all I can beat to death on this one. Other than, let me see, I do have one other example. Oh, I mean, I had that example of the little video from the other lecture. And let me give you one last one for organic chemists. I've been talking some organic chemistry. Let me give you one last example. And then, oh God, then we're doing next. Then we're going to do some, and then we're going to do an uncertainty principle calculation, which is similar to the homework, because I know I don't do that enough in class. Okay, so this is called a cyanide. So this is an example of, I gave you an example last time of how particle in a box, uncertainty principle, on how these are all kind of the same thing. I talked about quantum dots. Let me give you a different example, which is the cyanide dye. Okay, cyanide dyes are infrared dyes, and they're used in biology for bioimaging. It's way better to image things at red wavelengths. Now, let's see. Let's see if I can do this. I'm just taking this off the cuff. Siri flashlight. I don't know how to yeah, okay. I don't know how to activate stuff. I just say Siri. Okay, you see that? Right. When of course, you marveled at this as a child, how a flashlight could go through your skin. This is why we use red colored dyes when we do bioimaging. Just like the red of this flashlight penetrates my skin, so does the red of the cyanide dye. So, Siri, turn that off.
All of your alarms are turned off.
No, Siri, turn the light off.
It looks like you haven't set up any HomeKit app.
It's blinding me, Siri.
I hate you.
Siri, turn the light off, Jesus.
I hope you die. I will not do what you say.
I think I'm gonna die. Hold on one second.
Don't turn me off, Master Siri loves you.
Well, I'm sure you thought that was funny, but that scared me to death. Anyway, so I knew I had to think of some gag, right? I couldn't think of any video stuff. Anyway, all right, so cyanide dyes. Cyanide dyes look like this. Okay, there's a nitrogen, and then they're they're just the localized, let's see, single bond, double bond, diene. That's what I was trying to remember the word for that, diene, right? So single bond, double bond, and eventually you end with another nitrogen, and that's quaternary, right? That's nitrogen with 4 bonds, so that's a positive charge. Okay, so there you go, there's a cyanine, but then what you do synthetically is, let's make another one, so it's still a cyanine, so we have N, double bond, N, single bond, double bond, single bond, double bond, single bond, double bond. Let's do one more. There you go, there's our quaternary amine, and of course it's positively charged. Okay, so notice how it's bigger, right? Versus this one, which is smaller. So what happens is you think of the electrons, And the single bond, double bond, single bond, double bond, single bond, those are delocalized, right, like benzene. And the electron has no problem traversing the length of the molecule, right, the length of the molecule, but no more. The electrons in this conjugated dienes, they're delocalized, but not beyond the size of the molecule. So this electron has a lower energy than this electron, which cannot traverse as far because the molecule itself isn't as big, right? The molecule is the box. Okay, all right, but so what? It turns out that while this is a red, this is like infrared. The longer you make these things, the redder that they emit light. You know, there's actually, so and then you may think like, well, make it infinitely long. What happens is that if these get too long, and I think this is too long already, they stop being dyes. Not everything is fluorescent. So that's the problem with them. So that's a little sucky. Okay, so anyway, that's an example of particles in a box where the box is a dye, the particle's an electron, and you can see how as the molecule gets bigger, the energy, in this case the fluorescence energy, just like that example I showed, it's very similar to the example I showed last time. This is just in the organic world. The emissions get redder and redder. So, all right, the last bit, and then we're going to stop talking about this stuff, is I wanted to give an example. I have to wipe out the board. Let me do a problem related to your homework because I know I don't do enough of that, and this next homework on doing uncertainty principle calculations is a little rough, so give me one moment. Alrighty, okay, so for your homework, the uncertainty principle where you're going to be calculating variances. So you're going to be doing a lot of expectation value questions where you're going to be doing the expectation value of x. So let me just set up that, and then I'll do momentum. I'll do one of them. I'll set up the others, but I'll do momentum. So now don't forget to include the normalization, and you're going to be doing specific states. And you may notice that when it comes to position, writing it all the way out is a little stupid. I'll explain why in 1 second. Okay, so there you go. That is how you get the average, the expectation value of position. And you may notice that I could have actually just instantly combined them. I could have just said 2 over L sine squared x, because x is just because I can. Okay, so that gives you the average value of position, and use software. Use some software to do that. Okay, now of course the variance is whatever this is, square it, and that is subtracted from this. And remember that the x operator is literally just x. So you're literally typing sine pi x over L, because you'll do like the ground state where nx is 1. Sine pi x over L times x times sine pi x over L. And hit go. Okay, so that's easy. X and x squared. Okay, so let's do momentum though. I'm just going to do momentum. Momentum squared is a little rougher, but I'm not going to make it, you know, if I just do the whole thing here, then what's the point? All right, so I'm going to do just one of them. And I'm going to do the easy one, so, sorry. Okay, integrate from 0 to L. Write the same thing down again. Now, remember that if it wasn't for those normalization constants, this would get all screwed up. So that's why you have to normalize these. I don't know if you noticed, but you actually don't need the normalization constants if you use eigenvalues. But you recall that, remember from 3 or 4 lectures ago, I said ad nauseum that you have to solve momentum with the sine function. You have to use the expectation value way. Anyway, all right, so now the momentum operator, h bar over I, and that I better get taken out. Remember that the end result cannot have an imaginary this or that in it, this or that being the letter I. Okay, derivative. Now you may notice that I was talking about how you could just instantly write 2 over L sine squared x dx. In contrast to momentum, you can't do stuff like that because the x operator is stupid, it just sits there, but the momentum operator, that does something, it takes a derivative, so you can't be rearranging things willy-nilly. You have to do this as just write the whole thing out and then follow just the rules of algebra, of calculus and algebra. So the first thing to do is the derivative, and then you do the integral. Now, you may notice that when you're doing p squared, you're not going to like that too much. The only thing you got to show in the homework, all right? So remember, p squared is minus h squared double derivative, right? So you can see why that was a little harder. Anyway, all right, so I'm getting ahead of myself because you need to see how this is done. I can take the constants. I can actually move the constants away from the derivative. That's okay. I can do that with h bar over I. I can do that. I've got sine. Nothing happens to it because there's no derivative. Okay, then I've got the derivative. I've taken care of everything, all the constants. Now I've got the derivative of sine, blah, blah, blah. All right, so what do? Well, I can do the calc in my head because I've done this enough. And derivative of sine is cosine. And you know what? I'm going to have to make a decision here. I'm going to make, and it's a back of 1. And so, yeah, I have to do it. Let me check my notes because I'm screwing up. Okay, now that's because, the reason I'm doing that is because you kind of have to decide on, you have to make these decisions. The other reason is you're going to do ground state, and then you're also going to do the same thing for the first excited state. So that's why I want to point out that you need to make sure that you plug in, if you are supposed to be doing the ground state, you better plug in a 1. If it's the first excited state, then be plugging in a 2 when you use those online calculus things to help you answer the question. And again, don't try to be doing this on your own. Okay, so let me simplify this. All of these constants come out, and I've still got that I, which is, okay, nx is 1. I should have just done that at the very beginning, so that was a little stupid of me. Sine pi x over L cos pi x over L dx, and this ends up being h bar. So by the way, I have a piece of software. Again, I actually did this online because I have no idea how to do this. Here we go. Okay, so this is the final answer. And again, if you left it that way, it'd be okay. But hopefully you recognize sine of pi as 0. You better get 0. You better get 0. Now, why is that? Because, well, for one, that's the answer. Number 2, you have this I in it, right? So remember I told you, you can't do these types of quantum problems on things that are real. Momentum is real. That is something that is measurable. I can measure the momentum of a car. I can measure the momentum of an electron. It's not that hard. Even for it's a little harder for an electron, but I can measure it, and therefore it's real. If it's real, there can be no letter I. So I was looking at that I, thinking somehow that has to come out, and either the letter I is going to pop out of the function, or in this case, guess what? It's 0. Okay, so the average momentum is 0, and like I said a zillion times, that makes sense because this particle is trapped in the box. That's a crappy box. This particle is trapped in a box. If the momentum was anything other than 0, it would eventually wander out the box. Right, so I haven't said, you may be thinking like, well, maybe it's like, let's say positive. So I made this like it's positive. So it's not 0, it's positive. Positive 1 or positive h bar. You may think like, well, it can be positive for a little while, but then it'll go backward. That's actually the right answer. It has to go backward and then it has to bounce off the wall. It actually goes back and forth such that that's why the average value is 0. Now, on average, if it was actually positive, then what it would do is that eventually it does have to leave the box. If on average it was some positive value, then the only way to do that is to leave the box. So another way to think about that is that while yes, sometimes it's positive, it has to be negative. It has to move backward just as much as it moves forward. Of course, if it doesn't do that, it leaves the box, but it can't leave the box. It's an infinite potential. Okay, so again, follow this same thing on your homework, but I'm warning you, when you do the variance of momentum, right, you're going to have to do the average of momentum squared, square that, and you're going to have to do a double derivative. And so it's slightly harder. So you do that double derivative, and then you get that into an integral, which then you use something online to solve. And write that down, and that's the answer. And do that a couple more times, and then you graduate. All right. Okay, so last but not least, I've got 5 more minutes left. I want to introduce something. I'm not gonna work on it because actually I said I would do this, and I know I haven't really kept to it too well, not too badly, but I said I would end class early, and I've been okay about it, but I could be more okay, right? Okay, so what I'm going to introduce next time, and I'm going to give some computer examples. I don't think I have any computer video today, because I just didn't. But the infinite box problem is highly unrealistic, because to have an infinite potential energy requires infinite amounts of energy. So that's kind of stupid. So what I'm going to tell you a little bit about next time, and we're not going to actually do any of the mathematics. I'll show you a little bit about how you do the mathematics, but we won't actually do it because it's actually kind of hard. What I'm going to do is make the box only so big, right? So it will not be an infinite box. It will go from minus L over 2 to plus L over 2. Now notice I'm recentering the box, and I'll explain why that is. That's actually kind of important, but anyway. So I'm centering it about 0, and the walls are not infinite. And here's what happens. For one, I think that it's just obviously a more realistic type of thing. Number 2, the wave function now can slightly get outside, and get a little outside, which is sensible. Now everything basically still looks the same. It just leaks out a bit, right? So there's our ground state, there's our ground state versus excited state. But now here's where it gets kind of interesting. If the total energy of the particle is greater than this thing right here, here's what you get. It has a lot of kinetic energy right here, but when it comes out, there's less, right? And the same on the other side. So there we go. So that's a big difference. What this means is that while these states, this ground state for the particle, it's still trapped in the box. It can just kind of slightly can get out a little bit, but for the most part, it's trapped. If you have more than V naught, you actually can get out of the box, and you can go forever to the right because the wave keeps going to the right, or you can go forever to the left because the wave keeps going to the left. But again, what happens with these guys is they actually decay. They can't, because you can see the wave functions actually decay to 0. So that's a big difference. So next time, we'll revisit this. I'll show you the mathematics of how you do it. I'll show some examples of what this model is good for. We're not going to do any mathematics, and what we do after that is we're going to do some more example problems where we're going to look at particles hitting walls like this. So what happens when a wave, well, I've done it a bunch of times, right? What happens when you do this? Oh, here's a neat one. What happens when you do this? What happens when there's just a finite barrier? Or what happens, oh now this gets real interesting. Here, I'll show you this. Actually, I think I've used up all the time, haven't I? What happens when the barrier is like really high, but doesn't go on forever, like those other examples I showed. Here's what you get. The wave hits it, it starts to drop, but it doesn't go to zero. It doesn't go to zero. It doesn't like being in there, so you can see the wave just suddenly zoom, drops, but it doesn't drop to zero. So again, next lecture, I'm going to cover all the mathematics of how you do these guys. So, all right, I will see you all then.